Alright, in the first sort of block of the exam, we've got 6 short answer questions. We're asked to identify these 3 basic types of lateral force resisting systems. We have a brace frame, shear wall, and moment resisting frame, left to right in order. Brace frame looks like a truss. Doesn't matter if it's pin or rigid connected. If it looks like a truss, it behaves like a truss. You have a shear wall system where you've got the beams and columns infilled with a specially detailed, usually reinforced concrete wall. Could be, though, a specially detailed timber type wall, and also it could be a reinforced masonry wall. Every once in a while you actually have a steel wall in there, but usually that's reinforced concrete. And then we have a moment resisting frame where the beam column joints are designed and constructed such that we can transfer moment between those two, and this is a highly flexible system. We don't have any structural elements in the middle, and that's what makes it so flexible compared to these other two. The next one is about identifying what turns out to be these shear walls. Now, certainly we don't have any diagonally braced frames in here. These open panels tell us that we do have some sort of a wall system. We got these openings that are in the wall system, and shear walls are so much more stiffer than, say, these moment frames that anytime you have them, the building is going to be dominated by that kind of behavior. Right, so this thing is a shear wall. It's the vertical element, the lateral force resisting system. That shear wall will respond to the lateral loads that get transferred to it by the diaphragms through bending and shear deformation type behavior. The third item is going to focus on this horizontal planar element. Yeah, the planar spelled incorrectly. That planar element is connected to the vertical elements in the lateral force resisting system, and it collects load from then these other little pieces that take, say, for instance, the pressure and the effects or force effects of the wind. Those little pieces go up and down in terms of transferring load. Then that means that we have, in effect, a whole bunch of basically distributed forces that are imposed on this diaphragm. Diaphragm, through bending action, then is going to transfer those effects down to the over to the vertical elements, right, which will take it down then to the foundation. Our role as structural engineers is ultimately to provide a safe and economic load path. We do that in the environment where we're using materials that can only be estimated, that someone is going to use those materials to build real structures. Those real structures can only be approximately analyzed to withstand forces that are not accurately known, that are highly variable and highly uncertain. Right? So structural engineering is the art of doing all that, and we do that so that the responsibility to the public and the client is satisfied. Both to the public, for sure, that is the safety, but the client is not only safety but also economic in how we do things. And ultimately, as structural engineers, then we're doing that. We're creating that safe load path. If we can do that, we have executed our primary responsibility. And then on item 5, we're looking at the vault walls. We're looking in plan view. We've got this cover over that, and the question is how do we know to model that as a one-way or a two-way slab? That key thing is that the ratio between the long span to the short span should be about 2 to 1 or larger if we want one-way behavior. And so we can take sort of a 1-foot strip or 1 meter strip along the short direction, and with this 2 to 1 ratio, then that little beam strip will behave like a one-dimensional beam, one-way bending, till you get out to these edges where then you'd have inevitably you're really going to get some two-way action in these little triangular regions. We might, though, for the most part, still, depending on just how large this ratio is, we still might really consider this as 2 to 1 kind of behavior, but truly when we get out to this edge, things get to be a little bit different. And then the last of the short answers are what's the philosophy behind these various different load case combinations? We have dead loads, live loads, arrival loads, snow, rain, wind, earthquake, lateral earth pressures, all that stuff. We do not look at that as all those extremes happening at the same time. Instead, in each of these situations, as in load case combination, we'll look at one of the load types being at its anticipated extreme value, whatever that might mean, while the others are at an arbitrary point in time value. And so we're setting these values in a probabilistic manner, those extreme ones, and these others are the highly correlated values that might be happening simultaneously.